Alright guys, May 17th through the 21st, lesson 3. This is the last week of new lessons. I know you're disappointed in not having to hear me anymore. No, I'm just kidding. I miss you guys and hopefully get to see you next year. But we're going to be looking at these two lessons this week, and then that's it for new material. Guys, you have until May 26th to make sure you get everything turned into me. I have to have grades done by May 28th. So May 26th is the absolute last day that I can take anything. So if you're missing anything, get it to me as soon as you possibly can. Let's go ahead and look at this. So we're going to complete parts 1 through 3 of the table for each of the following figures in A through D. 1, we're going to determine the area of the figure pre-image. 2, we're going to determine the scale dimensions of the figure based on the provided scale factor. And 3, we're going to determine the area of the dilated figure and then answer the questions. Alright, so let's go ahead and look at the first figure. If you remember, the area of a triangle is 1/2 base times height. Alright, so let's go ahead and look at 1/2 times 8 times 3. So 1/2 of 8 is 4. 4 times 3 would give us an area of 12. Alright, if I am going to dilate my figure by 3, that means I'm going to change the sides by 3. So 8 times 3 is 24. And 3 times 3 is 9. So now we need to find the area of this. So 1/2 base times height. So 1/2 of 24 is 12. And 12 times 9 is 108. Alright. So then the ratio would be the area of the similar triangle, so 108, over the area of the original, so 108 divided by 12 would equal 9. Alright, let's look at figure number 2. So we're going to do 1/2 base, which is 5, times height, which is 3. 1/2 of 5 is 2.5 times 3 would give me 7.5. Alright, so my original figure has an area of 7.5. Alright, I want to dilate those sides by 2. So it's going to be a 10 by 6. So now I have to use the area formula for that. So 1/2 times 10 times 6. Alright, so 1/2 of 10 is 5, times 6 is 30. So we'll go back here, and our area for the similar figure is 30. Alright, and then I've got my similar 30 over my original over 7.5. Alright, so I get 30 divided by 7.5 is equal to 4. Alright, let's look at the next triangle, or the next figure. So here I have a parallelogram. Alright, in order to find the area of a parallelogram, I don't know if you remember this or not, but to find the area of a parallelogram, we do base times height. Alright, so we've got area equals base times height, so that would be 5 times 4, so that is 20. Alright, now we want to scale this down by 1/2. Alright, which means I'm going to divide each of these in half. So now it's going to be 2.5 by 2. Alright, and then to find the area of this parallelogram, base times height, so 2.5 times 2 is 5. Alright, so then I've original, and that reduces to 1/4. Alright? And then the last figure, parallelogram again. So base 3 times 2 would be 6. Alright? And we want to scale it down by, well, we actually want to dilate it by 3/2. So I have to multiply 3 times 3/2, which would give us 9/2. And then 2 times 3/2 would give us 6/2, which is 3. Alright? So I've got 4.5 by 3. And it's just easier to write it as 4.5 by 3. Alright, so in order to find the area of that, multiply those together and I get 13.5. Alright, so then I've got 13.5 over 6. I don't know if how this is any easier. But what I can do is 13.5 divided by 6. I get 2 25/100, which is 2 1/4. Alright? Or 9/4. Alright? Alright, so looking at this, we want to look at the next question. Make a conjecture about the relationship between the areas of the original figure and the similar figure with respect to the scale factor between the figures. Alright, well let's look at the area of our original, look at the scale factor, and look at the area of the similar figure. Alright, and then look at your scale factor. Alright, they want us to talk about this. Well, let's just take the first one. I have 12, I have 108. I'm looking at a scale factor of 3. Look at the ratio of my areas. It's 9. It seems as though the value of the ratio of the area of the similar figure to the area of the original figure is the square of the scale factor. Look, square that scale factor, I get 9. Square that scale factor, I get 4. Square 1/2, I get 1/4. Square 3/2, I get 9/4. Alright? So the ratio, alright, the ratio of the area of the similar figure to the area of the original figure is the square of the scale factor of dilation. Okay? Alright, we have conjectured that the relationship between the area of a figure and the area of a figure similar to it is the square of the scale factor. Alright, so let's kind of look at a figure here for just a moment. Sorry. Alright. I'm going to try to draw this. I'm not the greatest of artists. Alright. Okay, so we'll call this polygon Q, and we'll call this polygon P. Just for... Alright, so polygon Q is the image of polygon P under a similarity transformation with a scale factor of R. How can we show that our conjecture holds for a polygon such as this? Well, polygon Q is the image of polygon P under a similarity transformation. Alright, we can find the area of each and compare the area of the two figures. Alright, how can we compute the area of the polygon like this? Well, we can break it up into triangles. Can any polygon be decomposed into non-overlapping triangles? Yes. If we can prove that the relationship holds for any triangle, then we can extend the relationship to any polygon. Alright, so let's talk about the scaling principle for triangles. Alright, if similar triangles and we'll just say S and T. Alright, so if I have similar triangles, S and T are related by a scale factor of R, then the respective areas are related by a factor of R squared. Okay? So how do I prove this? Well, let's look. Alright, so let's say that I have triangle S. Alright? So here's triangle S, and here's triangle T. Alright? To prove the scaling principle for triangles, let's look at this, and let's consider this. So here's my base, and here's my height. Alright, and so then we're going to let this be, remember we have a scale factor of R. So we would be multiplying this by a scale factor of R, which means I'm also multiplying this by a scale factor of R. Alright, so let's look at the area of these triangles. So the area of triangle S would be 1/2 base times height. The area of triangle T would be 1/2 times RB, which is base, times RH, which is height. Alright? Which is 1/2 BHR squared. Alright? So how can we show that the ratio of the areas of T and S is equal to R squared? Well, go ahead and set it up. 1/2 BHR squared divided by 1/2 BH. Well, what is 1/2 divided by 1/2? That is 1. What is B divided by B? That is 1. H divided by H is 1. And then I have R squared. Well, what is 1 times 1 times 1 times R squared? That is R squared. So we have proved the scaling principle for triangles. Alright, so given the scaling principle for triangles, can we use that to come up with a scaling principle for any polygon? Well, we said that any polygon can be divided into non-overlapping triangles. So, we can come up with a rule for any polygon. Alright, so here's what we can say. If similar polygons and we'll just say P and Q, alright, are related by a scale factor of R, then their respective areas are related by a factor of R squared. Alright? So basically we're saying that we can take this and use this for any figure. Alright, let's go back to polygon P and Q. Alright, so I can divide this into non-overlapping triangles. Okay? I can divide this one into non-overlapping triangles. Alright? Each of the lengths of the polygon Q is R times the corresponding side of P. Alright, so we are by a scale factor. So the area of the polygon P would be, so here's a triangle, 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 triangle. I don't need this line here. So the area of this polygon would be, the area of polygon P would be triangle 1 plus triangle 2 plus triangle 3 plus triangle 4. 1, 2, 3, 4 plus triangle 5. Alright? So, let me get another sheet of paper here. So, by a scaling factor, alright, so the area of P was triangle 1 plus triangle 2 plus triangle 3 plus triangle 4 plus triangle 5. So by scaling factor, that means I am multiplying each one of these triangles by a scaling factor. Alright? And it is R squared. So, to find the area of triangle Q, I would do this. I would have to multiply each one of these triangles by R squared, okay? But don't flip out, because look at this. This is the same thing as saying R squared times T1 plus T2 plus T3 plus T4 plus T5, which is also the same as saying I can do R squared times the area of P. Alright, so I can do the area of P. Alright, so let's use this. So we've got rectangles A and B are similar and are drawn to scale. If the area of rectangle A is 88 millimeters squared, what is the area of rectangle B? Well, we don't know what the scale factor is. So we've got to find our scale factor. Alright? So, to find our scale factor, we're going to do this. I'm going to take my dilated over my original, because I went from 16 millimeters to 30 millimeters, and I'm going to figure out what that equals. Alright, so 30 divided by 16 is 1.875. So that is my scale factor. That is what I've done to everything. Alright, so the area scale factor. So my area scale factor is 1.875. That's my R squared. Alright, so the area of B, would be my R squared, 1.875 squared, times the area of A. Alright, so I get 1.875 squared times 88. Alright, well, let's do this. 1.875 times 1.875 is 3.515625 times 88 gives me the area of B is equal to 309.375, and that would be millimeters squared because I'm dealing with area. Alright? Let's look at number 2. Figures E and F are similar and are drawn to scale. If the area of figure E is 120 millimeters squared, what's the area of figure F? Once again, I need to figure out my scale factor. Alright, so our length scale factor I went 15 and 2.4. Alright, so we'll divide 15 divided by 2.4 is 6.25. You know what? E is my dilated. So that's not right. So my original and not only that, guys, I failed to look at this. I got centimeters there and millimeters there. So we've got to look at this for just a second. I need to change 2.4 centimeters to some amount of millimeters. Well, to do that, I'm going to move my decimal point one place to the right, and I get 24 millimeters. Alright? So now I've got 15 over 24, because this is my small one. Alright, so 15 divided by 24 is 0.625. So my area scale factor is 0.625 squared. Alright, so the area of F is equal to 0.625 squared times the area of E. Alright. So, the area of E was 120 millimeters. Alright, so let's figure this out. 0.625 times 120. I get this. 46.875 millimeters squared. Alright, so how can we wrap this all up? So if similar figures A and B are related by a scale factor, here we're not looking at triangles, rectangles, we're just saying any figure. If similar figures A and B are related by a scale factor R, then their respective areas are related by a factor of R squared. Okay? Alright guys, that's pretty much it for this lesson. We have one more lesson and then we will be finished. Have a great rest of your evening.